engaging. And we're fortunate to have here those whose educational background and professional experience let them know all and a little bit more about physics and physics education. And those whose vision and passion make change in physics education.
Okay, thank you all for being on this panel. I'm sure we can raise some sparks about physics education. You can see that the subject has been chosen to be a bit provocative because for many students, physics is the most, not us, the most dull and boring subject of all the science subjects. Now, I'm going to ask my panel members, maybe starting about Mita, give me like a 3-minute statement that you want to say about the topic.
First of all, thank you, Pro Scientific, for inviting. So when I first received the email, it seems innocent enough, but I didn't read it carefully. I thought I would be the audience because that's my natural ground state. So I don't expect to be in an excited state. So I will just borrow a bit of energy and do a demo. Okay. Okay, so usually we have this demo in school. Alright, it's a very simple one, and of course when we show this to students, right? Okay, so we just simply do this, and we often ask them like, okay, so you know, what is this all about? Alright, and most of them would tell us the correct answer, and that is very good, center of gravity. Okay, so of course if you ask them like, you know, so what's the center of gravity? Then they'll rattle off from the textbook, you know, from the memory and so on and so forth. Okay, center of gravity is the point through which the weight appears to act through. Okay, all right, good. Okay, so then after which, okay, so what we do? Okay, so we will turn it around and we ask the next question. Okay, if I let go of my left hand now, what will happen? What will happen? 3, 2, 1. Okay, alright, okay, so 3, 2, 1. Okay, so 90% of the students will tell us, oh, this thing will drop off. Okay, so that's very interesting because they know the definition. Alright, and I told them, actually, you know the definition. Alright, okay, so this is the point to which, this is the point, right? To which the weight appears actually accurate is slightly below the beat, but never mind. Alright, okay. So, alright, okay. So this is the point. And you say that the weight acts through here, right? Okay, and then, you know, so if you draw a free body diagram, how is it going to be like? Okay, so it's going to turn over. Okay, so we can slowly lead them to the answer, but at the moment when they actually see this, they assume that you kind of fall off. But yet they know the idea of center of, supposedly know the idea of center of gravity. So there's a bit of disconnect there in terms of actually knowing the definition and actually getting the idea correct. So this is something that, you know, we in the science demonstration lab would like to explore in terms of getting more of such demonstrations and more of such ideas, or rather ideas of science communication, of course. Yeah, so so that's what we have been trying to do. So maybe we can have more comments from the audience, you know, after this. All right, thank you very much.
Please.
It's on already.
Yeah. I checked this morning what time are we supposed to finish today. And I was told 11:30. 11:30.
Yeah.
So I can tell grandfather stories. So I think this is one opportunity, you know, to share many of you who do not know my background. Guess what? There's one thing common between Andrew and me. Both of us were teaching scholars. I got a teaching scholarship to study physics, you know, at Singapore University. And at that time, if you do well in A-level, you come in as a super fresh. You come in direct in second year. After third year, you get your degree, first degree. Then after the third year, you get your honors. So you get finished in 3 years. So that's where I met Bernard. At that time, when you're an honors year, you're supposed to share with your juniors. So, demonstrator, and you go to the lab and working in the sense that, sharing with what you learn with the younger students. And then there was a problem. The convent of the Holy Infant Jesus, Victoria Street, was starting the first class in science for the A-level. They couldn't find a physics teacher. So my sister was the chemistry teacher there, so she spoke to the mother, superior, whatever. Said, you know what, my young brother is doing physics in his honors year, and he just will be able to teach physics. I said, yeah, they can't find a teacher. There was this young man, take him, so I became the first male teacher in CHIT. And guess what? I couldn't understand why the young girls do not understand what I'm trying to do. Then I realized how stupid I was. Because I was not in their shoes, looking at the subject trying to, to learn. I was looking at myself trying to push down ideas. So first lesson said, always try to be on the other side to say, actually, how best you can. But anyway, I taught for 1 year, I graduated. Second year, well, I got to serve my bond, right? So I was employed as a temporary teacher. Because you are not qualified for a teacher until you get a diploma from the Teachers Training College. So in the morning, you teach as a temporary teacher. Afternoon, you attend class, learning how to teach. And near the end of the year, the Science Research Council was recruiting graduates to be scientists in the radio and space research station. So they are doing two types of research in Singapore. One was measuring the ionosphere. How does it vary with time of day, and how does it affect radio transmission? So that was done in Bukit Timah campus. The other was tracking the satellite that they have launched with American UK2 in Sembawang Air Base. So that's how I learned about tracking satellites, collecting data, MPEGs, tape recorders recording our data, at Sembawang, and how to measure ionosphere in Bukit Timah campus. Then the Ministry of Defense at that time was MID. Said, why are you wasting time with the British? Singapore need you, join the army. What am I supposed to do in the army? I'm supposed to do research, and there's definitely no research in the army. Right? Say, you know what? How about doing test and evaluation? What about test and evaluation? Everything we buy, we test. Oh, okay. Normally we test according to specifications, right? Where are the specs? Then you look at what specs? You write specs. So I wrote the specs, so like uniform, rations, bullets, land mowers, armored cars, and so on, and I tested also. So that's my start. So I never went beyond teaching physics for about 2 years. And after that, I worked my way, in defense, doing various things. And come to the Bernard, say, why we together, physics, go worrying about physics? It's because we found that engineering faculty did not require physics as a prerequisite for entrance. And you started, and you followed. How can you study engineering without a grounding in physics? And well, they look, we have to compete. This is a free market for students. So no physics is okay. We teach you. When you come in. So obviously it's wrong. So since then we are working hard at ministry, see how to reverse the situation. So every few months I have a chance, I push something. So the next chance I have is 29th of August at a lunch going to be hosted by the PS of Education, Regent Hunt, and the subject which I push on against it. Well, you know all statistics, you know what happened. That actually our youngsters, they can take physics or take a softer subject. What is that? Biology. Which one is easier to get A? Biology. How many A's you want? 4 A's. So therefore don't take physics, take biology. So we found that since year 2000, the number of students that have taken out biology has gone up, and the number of students taking physics has gone down. So now we still produce 5,000 engineers a year, of which I would say that maybe 1/3 of them did not have a physics education at the A level. So how to change things? So I don't know. Just keep complaining. Hopefully, some boys will hear say maybe it's right. Time to change. That is make. Who am I to friend to? He's in charge of curriculum development and rising star MOE. Few things happen. So, thank you very much.
That's quite a tough act to follow. But maybe just okay, yes. Actually, that
to Oxford.
okay. So yeah, I guess I have the privilege of actually also being quite similar of getting that OMS teaching scholarship. I remember I applied for the my first choice actually was the police scholarship because I didn't want to go to army. So police actually makes sense because you're protecting the country without having to kill people necessarily. But then I think it's quite a similar situation. At the end of the interview, they said, "How about being a teacher?" Okay, but actually teaching was my second choice, so that's I definitely took it. So I'm very grateful for that, and also got a second teaching scholarship to do my DPhil in Oxford as well. So that was quite nice. To answer, okay, I don't know. I guess the panel sort of has started already, right? Because this idea of well, the fact is in HQ as well as in schools, I think the physics teachers, their colleagues are bio teachers. So we have to be careful. We want a well-rounded education. We need all kinds of talents, right? We need people who are passionate about physics. We need people who are passionate about chemistry. People who are passionate about biology and all the other subjects that we have in schools. I think to keep myself from rambling on, because I did think about this topic quite a while. It says, can teaching physics be fun and engaging? I think can, of course, can, right? The other thing, but my natural instinct actually was, can learning physics be fun and engaging? And I realized actually that's not the question, right? Because it's a different question, right? You are talking about teachers' experience versus the student's experience. Well, as a student, for sure, my learning of physics was fun and engaging because physics as a discipline, as a subject itself, is amazing. As a teacher, what I found fun and engaging in my experience as a teacher, right, just one person's experience, but I found that how I got this sense of physics being fun and engaging was when I challenged myself. It's actually not so difficult to go in front of a class and just teach everything like according to the textbook, right? I think it really starts becoming fun and engaging when you try to do something different, when you try to really speak to the students in a way that makes yourself uncomfortable. Because the safest thing is always to say, oh, Newton's law, just accept it, it's like that, don't ask why, right? But I think when you start asking why, then you yourself also get curious, you get engaged, you get uncomfortable. But I think this kind of discomfort, this kind of not being sure what it's about is really, as I think Kim Yong's demonstration showed, right? That my instinct was, I'm going to catch it, right? It's going to fall. Somehow it's going to fall. Of course, we don't know whether it'll fall this way or that way, but it was going to fall. But I think when you have things like that, then you okay. I have something here. So it's meant to. I wasn't sure what the layout of the room was like, so it was like I could catch everyone by surprise, but this one is no, this is no, it's just
Oh yeah.
fun. Okay, I practice it. It worked mostly all the time, but yeah. There's the other thing about demonstrations as well, right? You can all sorts of stuff.
Tangle back.
You can, yeah. You can. The nice thing about teaching also is you can tell lots of stories and so on. But I think I'll just say one last sentence, right? Which is that I guess we have to ask ourselves, where is the future of physics education as well? Like increasingly we are aware that I don't know, the world is wanting quick results. You know, the world is wanting fast solutions. Machines can do a lot of things better than us these days. When you put the words physics and education together, I think you naturally have this word education, which associates ourselves with human brains. Right? The act of physics education is a way of sort of getting new people, different people, the young people, to know more about the world, right? But there's that other aspect of sort of why is physics relevant anymore, right? And I think we have to ask these questions to ourselves because you know, the kids these days, when they see all the things that technology can do, there is a huge gap between sort of like using the technology and being able to develop the technology. And the danger many of them would have is, you know, they just take the technology for granted and not want to put in the effort to then develop the next iteration of the technology. So I think as teachers, we do, I think as we all agree, owe it to our students and ourselves, right, to find our own work engaging, to find our own work fun, because that's when we would really push ourselves. And then for students, they can also see that learning physics can be fun and engaging, and then whatever they do with physics can also subsequently be fun and engaging. Right? With that, I'll pass over to Shen Yong.
Okay. So actually, I didn't realize before this that actually now there are like a few of us with a common past. So I'm one of them. I'm a bit more clueless because I didn't know there's such a thing as a scholarship until I was JC2. Yeah. Then we have all these PSC, paper and pencil tests and so on. Yeah. Then I get more prepared. So I started teaching in Hwa Chong in 1998. So I see some of my colleagues here, former colleagues. Okay, and then I furthered my studies after my bond was completed. So there was then it was an 8-year bond. Yeah, for 3-year studies. Yeah, so I finished my studies and I managed to come back to Singapore. So I was looking for a job desperately actually. So actually I even contacted Andrew at some point. So he kindly appointed me to NTU. And it was just a small window of opportunity when because they were looking then for a physics lecturer, okay, for engineering students. And that's the job that I'm still doing today. Okay, so I'm teaching the engineering. In one semester, I'm teaching the engineering physics, engineering students physics. Okay, so one of the things, of course, that we do is a very big class, and as you have mentioned that these students didn't choose physics as a first choice. Okay, it's something they have been actively avoiding all their lives, and they don't have much choice because they somehow decided to do engineering. And so they have to pick up the physics and in a very short time. Okay, so one of the things that I have to think of was efficiency, because the course that I have to teach mechanics, electricity and magnetism, and thermophysics in 13 weeks. Okay, and this group of students, they have very diverse background. Okay, with students who have not done any physics-related things since Sec 2 actually. They avoided even combined science physics. Okay. So, and I have in the same class I have students who have done H1 physics. Okay. So it's actually a very big group. So of course the challenge is how do you teach in a way that the class can converge. Okay, and you need to prepare them so that by the end of the semester, when they go on to semester 2, they're relatively on par with the students who have done H2 physics when they go to semester 2. Okay, so teaching physics becomes an optimization problem. Okay, so there are a lot of constraints, but okay, so there may not be some actual solution, okay, to do this perfectly, but
it is an optimization. You can do to the best of the constraints that you have, and you have to think how to make things interesting for the students and see the relevance to engineering. Yeah. So the future of physics, we also need to look at the future generation. I mean, this generation, this is the mobile phone generation, mobile devices generation, and they're glued to the apps and so on. So one of the things that I tried and was very effective and I enjoyed teaching was actually to watch YouTube videos. Okay, there are certain categories of YouTube videos whereby it's actually very physics rich. Okay, but there's actually nothing to do with physics. It doesn't have a physics at all. Okay, so one category is road accidents. Okay, so there is actually a lot of physics involved, and you can actually show the students, and you can do some simple analysis. Actually, I was hoping to show some videos, but I'm not sure whether you will hook it up. Yeah. Okay, so let's see whether the physicists can do technology. Okay. Oops. So one of the most boring laws, I think you would agree with me, is Newton's first law of motion. Okay. And I was thinking how to make it interesting. So for the benefit of those who are not familiar with Newton's laws, so it says that an object at rest, for example my mobile phone, will stay perpetually at rest to eternity. Okay, and if it's moving, with a constant velocity, you continue to do so to eternity, unless a non-zero net external force acts on it. Okay, so I mean, the law itself is actually quite boring. Okay, but if you see it in action, let's see something that happened in Singapore. Okay, this happened quite near my house actually, and this is captured on someone's camera. So there was a bus exiting the expressway. Okay, so this is exiting BKE. So I think either the bus driver was not attentive, or he didn't somehow didn't slow down. So literally, the bus continued motion in a straight line. Okay, and it went over to the other side of the road. Okay, so actually, if you show this to an LTO student, you hear the grasp. Okay, and the same accidents, similar accidents happen. Okay, not just the bus. Okay, the same year that this happened, I found another video. Let me try to get this. Okay, my computer is acting out. Okay, so in the same year there was actually a train crash, actually around a bend, in Spain also. Okay, so if you look at these things, it's really Newton's first law at work. Okay, so of course this is seeing something that's external, and you think it will not happen to you. Okay, let me try another one. So actually, I have actually a lot of students, and this has happened to my friends also actually.
Okay.
So this is cycling, and it's downhill and it's round a bend. Okay, I think you can sort of anticipate what's going to happen. Yeah. So literally, this is Newton's first law at work. Okay, you just keep going straight. Okay. Because the force that you need to make yourself turn is inadequate. Okay. Actually, I have a group of students who went cycling in Taiwan, and something like this happened to them. Okay, not onto cars, but they nearly went off the cliff, actually. Okay. So I think in this case, there would be some relevance, personal relevance to the students. So I think that will sort of hook them on a little usually. Because sometimes they see, okay, you learn all these things, there's nothing to do with you. Okay, so if you show them something, and there's some relevance, that will get them more interested. So there are a lot of other examples. Okay, I won't show you, but there is something that I found quite interesting recently. Okay, and this is related to Newton's second law, actually. So one of the variant of Newton's second law is the impulse-momentum relationship. Okay, so if you exert a force over a period of time, you can change the momentum of a system. Okay, so I thought, okay, that's an interesting topic, and it is actually very important in car designs and a lot of other applications in engineering. Okay, but when I was looking on the internet, I found something very interesting. Okay, so actually I did specifically click on the word durian. Okay, because one of the things that you can apply sort of the impulse momentum relationship is to catch a durian. Okay, so if someone throws a durian at you, how do you catch it so that you have minimum injury? Okay, so these people made a sport out of this. Okay, so it's okay, so this is a new game that people invented in the village. And you walk further and further away from each other.
Move together.
Yeah, of course, we don't know this. We use water bombs in orientation. Okay, but the same principle applies. Okay. So I think you can feel it, right? Just look at it. Okay, so if you know some physics principles, it will be very good. So actually, before this, I have been showing another one which interests a lot of students. Okay, I think most of you, if you watch the Hong Kong drama, you probably would have. I have seen this. Okay. So I saw this when I was a little boy, and it left a very deep impression on me. So I decided, when I started taking physics, okay, I tried to understand what's going on here. Okay. So this is a martial arts movie. Maybe I can. Okay, so there is an entrance exam to be the apprentice of this Kung Fu master. You need to be able to catch a tofu without breaking it.
That's physics, yes. 我冇試多次。
It took me a few hours to get this. I borrowed the VCD from one of my wife's colleagues. Okay, that's the tutorial. And obviously, he didn't understand Newton's second law. Okay, and this is after he understood Newton's second law. Okay, so the Chinese. Okay, so this is the Ming Dynasty. So I think we were ahead of Newton actually. Okay. So first, I can't show students all the fun things. I need to show them some actual engineering application. So you can actually relate. Okay. So this is a car crash test. So you ask the students, do you want to buy a car where the front will collapse on impact, or one that doesn't?
To absorb the momentum.
So we think it's a lousy car because the front collapse, right? Okay, so hopefully after watching those Kung Fu and Durian videos, they understand that they shouldn't. Okay, so this is an example. I mean, you can actually go on all this YouTube and find interesting. Okay, I should show you. There's actually one collection. Oh no, sorry. There's an epic win and epic failure. Actually. Do you all watch those videos? Yeah, I watch it with my kids. Okay, so you can actually find a lot of interesting stuff. Okay. So this is someone from India. They're trying to lift up a motorbike onto the top of a bus. Okay. So within the same video, you have a lot of interesting other things. Okay, so this is at the top. Okay, so there's some physics in this as well. Okay.
How to put on your pants without touching. I see some.
So related to the Newton second. So this was another accident. It's a very interesting accident because the motorcyclist survived the collision. And actually, he actually applied Newton's second law, or the impulse momentum relation, to improve the chances of survival actually.
Are you serious about that?
And then he just walked off.
Look too cool. I won't try, that's why I asked the question.
So I think I made the point about social media and how there is actually a reach, a lot of interesting stuff that we can actually highlight to the students to get them interested and see relevance of physics. So I'll end off with an example that Kim Yong was mentioning. Because one of the things I noticed when my daughter was playing with this, the bottle flip. Okay, and it is something that can last longer than playing. It's more interesting than like a mobile phone game actually for her. Okay, so you're just trying to. Okay, obviously I didn't practice. Okay, so you're supposed to flip this, and you land nicely. Okay, and it takes a lot of practice. And it was one of the IYPT questions. Actually, it's not trivial. The physics behind this. So I think this is something that is not mobile devices related, but there are some simple games I think that can hook on the next generation. Okay, I think actually I should try this when I go home as well. Okay, so I think that's what I have to say. I think I've taken longer than I should.
Well, our four panelists have made the statements. Before I throw open to the audience, just very quickly say that I agree with all of them. You were saying that we need to have people relate physics to what they see around them. Of course, most of the time we see it in very sort of esoteric and glamorous kinds of physics applications, quantum computing, entanglement, gravitation like LIGO and all that. But sometimes I think that we need to have people open the eyes to physics which is just at the doorstep or around them. Your cyclist example gave me, a thought that I was seeing a video on trains the other day. The British invented, before high-speed trains were invented, the British were trying to do a tilting train because at a curve, of course, you want to reduce the lateral force. So if you, like a cyclist, a train can tilt, then of course you reduce the lateral force. So the British actually spent a lot of money on something they call the Advanced Passenger Train APT. And one of the major things they did was to make the train tilt to reduce the lateral force. It didn't work out so well because the parameters are such that a lot of people, even if they're tilting, got nausea and all that sort of thing. So anyway, the irony is that the APT was dropped and the replacement of that, the HST, the high-speed train, didn't have tilting. But the British then sold the patent for the toting train to Italy. And that resulted in a bunch of trains called the Pendolino. I think it's like the pendulum something toting. And the greatest irony is that the latest batch of British, there's no really high-speed trains, some fast trains which are running on the track that the advanced passenger train was supposed to be on, is actually Pendolino trains from Italy using British toting train technologies. But these are examples where you can draw from everyday life. And of course, mechanics and Newton's laws are an excellent way of actually drawing attention to things that happen. Another example I want to give is that 5 years ago, I had a cataract operation like many of us have to do. So when I got a bill for the lens that was implanted, I saw a model number. So I Googled it, like we all will do. And I found to my amazement, because I've not been following this contact lens technology, the lens that was implanted was not a refractive lens. It was a lens based entirely on diffraction instead of a glass. The lens are actually jagged edges, and the image was caused by diffraction from all of those edges. And you know the technology of plastic molding is so good that it's up to less than a micron. And then I found that my multifocal lens, which actually is bifocal, you get a far focus and a near focus, it's just a zero order and the first order of diffraction. So these are things that, I mean, if I didn't have the operation, I wouldn't have known about it, but these are things that we can use in our everyday life because we encounter them actually. So with that, let me sort of open the questions for the audience. I'm sure you have a lot of comments to make. Comments or questions? Yes.
Yeah, on
Can you identify yourself?
sorry, I'm Wolf from Science Center. A comment on relating physics to our everyday experiences. I find it increasingly difficult because technology is becoming more and more complex. How it's beyond a student to understand how a handphone works, right? So when I was young, generally our appliances devices were at a level that were still within the reach of easy understanding. So there was more of an everyday experience that we could relate to. I suspect this is one of the reasons why students don't see physics as relevant, because at the school level they don't get to a stage where they can apply what they learn.
Comments?
Whether MOE has any intentions of putting communications into the A-level syllabus, it's like it's like things like Wi-Fi, Bluetooth, and sorts. Okay, maybe not at a very deep level, but at an introductory level.
I guess we're open to it. I mean, in terms of our syllabus cycle, we do have a sort of a look at the syllabus every few years. I know that in the UK, the OCR, the Oxford Cambridge RSA qualification actually has, in fact, one topic on communications. Right? They talk about the information content in a bit, and then they relate that to CD encoding and stuff like that. So it's an interesting idea. Do you think it should be in? I mean, the problem, of course, in the school. Okay, I guess the whole thing about this trying to keep up with technology, keeping up with science is always going to be harder and harder, right? If we say we don't want students to learn more than they did 10 years ago, 20 years ago, then we'll always be sort of at this level, right? But if we say, oh, students now need to learn up to quantum physics, or they need to learn, all the way to this and that, then you start asking yourself, can we really squeeze so much education into so few years? So I guess it's always that balance. I don't know the sort of easy answer to that.
So I think you may have misunderstood. The headphone was just an example. For the same reason, for example, we teach students incandescent bulbs. That's at the level they can understand. Nowadays with white LED lighting, how do you explain to a student how a white LED works? That's completely beyond them, right? I even have difficulties. A lot of the students I encounter, they have never really ridden a bicycle, I had a highly talented, highly scientifically skilled student, who didn't realize what the gears on a bicycle were for. Simple machines. So basically, these everyday experiences are completely lacking because they're hidden so well away in modern technology. They're not accessible. At that point, they cannot see the link of what they learn in school to how is it really relevant. And that's probably not a very motivating experience. Because for myself, I always found the motivating part about physics is that it empowers you to do things.
Yeah.
I have a question. I'm one that never did physics, because it's difficult to solve. It's not that because I don't understand, not to be able to understand. Would it be possible that we mark the physics paper a bit more lenient? Lower the standard, so that there will be more who are willing to take
Actually, I agree with what you say. Yeah, I agree with what you say. I took a very long time to discover this thing. That actually, students have this. If you can do well in something, they become interested. So I think we need to make the barrier a little lower. Lure them in first before we up the standard. So that there's a wider population of students that would consider physics actually. So now I tend to not make my exam too hard. I feel bad because I destroy people's interest in physics if I make it too hard. I will make it, or at least it looks difficult and they can achieve it. Then they'll feel good, and then they'll want more. Yeah, so that's a very subtle balance that has to be made.
So otherwise, it's not fair. I put 90% of my time to do physics, and then to get an A. The other one, I take 50% of my time. I still get A. Obviously, I choose the softest option.
So adding to the bicycle question, actually, I also discovered this, but mine was probably more serious than the bicycle because I wanted to do a physics demo. Okay, that was back in 1998. I needed someone to blow up a balloon for me actually. So I just got a student from the front row. I was like, can you blow up the balloon for me? Then he hung there. He doesn't know what to do. Because I think he has been using a balloon pump all his life. So he has never blown a balloon with his mouth before. So we saw this actually, even striking matches. Okay, I mean, they use lighter. And even, I did an experiment also, that's involving some oil on a plate. So the students are supposed to wash it. And they didn't know how to wash off the oil off a tray. Yeah, so I think we should make our children's life less comfortable. They should do more things, try a variety of different things. Yeah, we should play more.
Just a comment on this. Recently we had the physics Olympiad in Adelaide, and the students didn't know how to use a camera. Use a camera. They know how to use the mobile phone, the normal. Yeah.
Sorry. Anyone? Yes.
So I guess there are 2 or 3 ends of the spectrum here which put physics in a very difficult place, right? On the one hand, you're competing with sciences like biology, which, we are interested in our bodies, right? And physics is competing with that. On the other hand, there is the issue of difficulty, as 2 or 3 people just mentioned. Physics is perceived as being very difficult. On the third hand, there's the aspect of usefulness. Like these days, a lot of my students, they just want to go do AI and machine learning because that's a skill that is very relevant to, jobs, which is what students care about. So how do you make physics fun and engaging for the student? Engaging in this case is how do you make them, a lot of our problems for the next generation have to do with solving physics problems. Like if you look at the National Day Rally speech, right? Half of the problems are physics problems. So how do you motivate the students to pick up the skills so that they can address these kinds of problems as opposed to, not as opposed to that. It's not like we're competing with AI, but how do you retain talent in physics?
That's a good point.
Yeah, very good points. I thought, let's see. Yeah, so because if you do a comparison, which we definitely can do in MOE, right? We see like there are all these subject combinations that the student can take. Every subject is different. I mean, maybe the science subjects there are more new developments happening. I don't know, but maybe that's unfair, right, for the humanities colleagues who might think that for whom, like, I guess there isn't such an explosion of knowledge as we've seen in the sciences. So how, and then at the national level we want everyone to all the grades have to be sort of like weighted evenly. You can't say physics is more important than anything else. So there's that struggle. But I think at the whole national optimization idea, we probably want everyone to find the right thing that they are good at, and to be encouraged and supported to go as far as they can in that one or two sort of areas of interest.
So, as school is one platform. I think school is one platform. I think there are also competitions actually. So if you want something that's a bit more multidisciplinary, okay, I think I can't fully address the problem that you posed. But I know of a professor in physics. So he's doing a very interesting research. He's recording sounds made by mosquitoes, okay, and using AI to identify the species of the mosquito by just recording the sound. So there's biology, there's AI, and there's physics actually. So there are actually avenues where you can actually put all your different skills together, of which physics is one of it. Yeah, but I'm not sure. Okay, so this is probably more at the uni level. I mean, yeah, to do such analysis. So I'm not sure whether we can find projects where you can tone down a little that is interdisciplinary in nature and involving physics, so that you'll see the relevance of physics.
So I haven't spoken much, so I should feel some quota. Alright, my own thoughts on this is that we should try to make physics fun and engaging at every single stage. And the reason for this is that I thought that even if at some stage, right, the student kind of drops physics, but this student may grow up to be a parent. And if this person becomes a parent and sees that his or her kids are interested in physics, then our hope is that this parent will actually encourage the kid to continue taking physics. Yeah, I mean it's just like like cooking, right? For example, I'm a chef. I cook lobster, right? But I try my best. I should. But if somebody comes along and says that this person is allergic to seafood, right? But at least if I make the lobster dish good smelling, right? It smells good. So eventually, when the kid grows up and and is not allergic to seafood, this parent still can encourage the kid to eat the lobster. If I cook a dish and it smells really bad, and then the kid growing up to be a parent think that this is terrible, no lobster for you. Yeah. So that's my thought. And further to that, I think somebody mentions about triggering interest. I mean, while it's true that in this age of tech, I think it's kind of difficult to relate some of very techy things to physics, right? And that's why Science Demo Lab, we keep a lot of old stuff. Yeah, and that's one of the things. And if any of the teachers here want a course for your students on how to light matches and clean fades and whatnot, then we can organize one. Yeah, for a small fee. Alright. So, sorry. Yeah. So every kid is, I would say, slightly different, and I think the trigger points are different. So I used to have a student, and this student is not interested in physics, not interested in anything that I show, demos, not interested in any video, probably not interested in Chinese Kung Fu and cycling. Yeah. But this student is interested in cosmetics. So there's this lesson where I taught optics, and I asked the class, okay, so if you want to look at pimples, right, you use a concave lens or convex lens. Sorry, concave mirror or convex mirror. Yeah. So after the class, this student actually came up and asked me, so is it concave or convex? So that interested this student. Yeah, I'm not revealing the gender. But you can see that there are different things that trigger different people, and I think it's up to the teacher in the class to actually locate some of these trigger points and make the lessons interesting. For a variety of students. Unfortunately, sometimes I succeed and sometimes I fail. So for example, that particular student, that was the first and the last question. Yeah, throughout her physics course.
The question relevance, I think, is very important. So the question is now, how to make physics still relevant? So give example. In my generation, when a car requires attention, you open up the bonnet, you change the spark plugs, then you add oil. Nowadays, you don't do anything. You just send a car servicing every 6 months and you don't even look under a bonnet. The old radios, our first radio, was a little crystal, a little whisker, and then you listen, I can hear. But now, when you look at a computer device, it's a chip. You can't get inside a chip. So actually, it's very difficult to go in the physics of it because technology has moved so far. Then the question is physics still relevant? Answer is yes. If you have to do things that create new things. So not everybody will be doing that. But the general population most probably will be happy enough to use the device wisely and as opposed to having to invent a new device. So our challenge is that how do we actually find those kids that have this motivation to create new things and give them all the opportunities to do it, as opposed to trying to bring everybody up at the same level. So the point about lowering the standard of physics, to make it interesting for them to do well, and because they do well, they want to do more. I think it's something we should be pursuing as opposed to try to raise the standard so high that only a genius will be able to do well. So the education of physics should be, my own will, is for the general public as opposed for the few specialists who are going very deeply in the subjects. Those kids by themselves, they don't need actually, the teachers. So I think the exciting thing for teachers is to understand that in this whole hours, we've got devices and various things, how to make it exciting that the fundamental principles still get across.
Maybe I could add to that. I think it's true that we I think the kind of, we don't need people who can change the spark plugs so much anymore. But you need quantum mechanics, right? We need people who can actually create the new the quantum computers. We need people who can do quantum information. We need people who can do those kind of things. And I guess increasingly we find that because of this specialization in the school setting, we are trying to ease the pressure a bit by allowing sort of everyone to find their own path. We want to support the students who can just fly by giving them all the resources that they can. And of course, digital technology allows us to do quite a bit of that. But of course, for the general teaching in a classroom setting, right, you do have to sort of cater to the whole class, and then we make sure that what we put into the syllabus is well considered, is is something that they can appreciate, and we definitely encourage the teachers to make it, connect, as all the presenters have shown, how to connect it to their real life, how to connect it to their own personal feeling, and impact them. And they are kids, so it's not rocket science, but in a way, actually, it's a lot of psychology. Right? It's how to get into the minds of kids. That's why teaching actually, it's not just about the physics, right? It's a lot more than that.
So I just want to make a comment on that. Because I'm in quantum information. Well, quantum information is one of the hottest topics in research. I think it's not the only topic. Particle physics, astronomy is what brings a lot of kids over here. So we should not forget that.
Yes.
Okay, maybe you say, because I think we have to.
So actually in this mobile phone here, there are 20 over sensors, and actually you can take a lot of readings. So now this becomes like a measuring device. There is a barometer in this, and if I move it up and down by 1 meter, you can actually tell the difference. Okay, but I never understood why we need a barometer on a mobile phone, but I think most mobile phones have a barometer. It has a hygrometer. Mine is special. It even have an ambient thermometer. Okay, so I'm keeping this Note 3 for a long, long time. Yes, extinct from and even the memory. If you want to talk about the memory, how do we have like 128 gig of memory in just this small little thing? It's a very interesting physics topic to talk about.
One more question. Two more questions. Very quick question.
I would just like to further on some of the questions that were raised, and we have actually been working with MOE, some of the JCs, with the CPDD actually. So we have taken some of these demos inspired by some of the things that I've been doing in Science Demo Lab, and this is targeting the modern physics demos. And what we notice is that when the teachers implement them at schools, they have tried it out, but there is a certain hesitation. The students find that ultimately how much of this is ultimately going to be coming in the exams. So this brings us back to the question of the exams, and I feel that while there's a lot of effort and energy that the teams put in making this physics engaging and fun, ultimately when it comes to ground reality, the priorities that students put, the parents put, the teachers put, ultimately comes to the exams. So I think that is there a way to, of course we can't get away with exams, we have to do them, but is there a way to restructure our approach to the way curriculum is thought of, not at the crucial O and A level years, but prior to that, at grade 11 kind of thing, and so on and so forth. So I think that is really necessary to bring about a change.
I'll just quickly take this one. Okay, I'm at a university, so I have this freedom. So I give class activity to students. They say it's not going to come in an exam, and I'm not going to do it. So I told them I will put it in the exam.
Okay.
I have a question for Dr. Ho. Do you have statistics in your engineering school, whether students who with a physics background do better than those without a physics background in your engineering school?
Without infringing, okay, actually there is one student there. Okay, he didn't do any physics. He did a diploma. What was the diploma? Accounting. Okay, he's one of the top students in physics. Okay, so maybe these are outlier cases, but I didn't have
engineering.
Yeah, engineering. I've not collected the statistics actually. So within physics majors, I look at some of the top students. They come from very interesting backgrounds. Okay, so they outperform the H2 physics students. I have students who did a diploma in communications, psychology, accounting, and they do better than students in H2 physics. So I'll take that as a homework.
So are you saying that physics is not necessary for people to do engineering?
Okay, so those examples I gave are in physics majors. Yeah. So if you didn't do physics before you come to university, and you just jump into engineering, there's a very steep learning curve in 3 months. It just makes your life very stressful. If you can survive the stress, so some of them do very well. Yeah, I have anecdotal cases, examples, but I do not have a statistic. But I'll take that as a homework because no, because the data are disconnected. I do not have their background. I only have their.
One more. One more. Anyone? One quick one. Okay.
I just want to make a comment. I'm Yap Won Bing from the statistics department, and I have always been envious of scientists, especially physics scientists. But you are. I think so too. Everyone agrees. I'm envious because you guys have demo, you have actual objects to show, but it's fun to see the anxiety within the community too. And from my perspective, I wonder if we can, or you can take a look at the role of mathematics in physics education. I think to most of us, mathematics, and this is true in my discipline of physics as well, mathematics to the instructors illuminates the practice. But from the student's perspective, it might not be. It might obscure the essential concepts of the discipline. So I think maybe we can all reflect on exactly, do we need to have so much mathematics, especially in the first few courses?
I think that will open another can of worms. Okay, I will ask each of the fellow speakers to give you 1 minute summary before we wind up.
I'm not actually asking for any response.
Maybe we start with 1 minute. 1 minute summing up.
Yeah, so I think we have actually brought out a few good ideas. Actually, for the question, the mathematics, the amount of mathematics needed, it depends also what is the learning objective of the course. Okay, so maybe we can postpone the mathematics a little. Okay, but actually I think in physics it brings out the beauty of mathematics. Okay, I give a very example, special relativity. We just start from 2 postulates and we end up with E equals mc squared. It's very, very clever. And I would actually want to bring a student through it. I think it's one of the greatest piece of art of the human mind. Yeah. So we will take some of the suggestions. I'll do some simple experiments in my classes.
I think I would just want to go back to the topic and just remind ourselves, of course, since most of us are educators, to take care of ourselves, right? And remember that we also have to find the fun and engagement, and not just think about the students who are supposed to have fun and engagement, but sometimes they don't. But then, if we can sort of take care of ourselves and make sure that we are having fun teaching, we are engaged in teaching, I think it will sort of inspire them to also take the same attitude towards life. I mean, because some of them, you look at they just want to get the results, they just want this, they just want to get a good job and so on. After a while, it becomes meaningless, it becomes hollow. I think the beauty of physics and astronomy and all these things, I mean, it's nature. It's what is so incredible that I think we are on this earth and we can't see any signs of intelligent life anywhere else yet.
Well, you can see that the science and technology is moving so fast. And what we learn is very soon obsolete within a few years. In order for us to be able to continue to progress, I think it has to be a lifelong learning. So I think it's very important to be able for teachers to keep thinking, how can I teach better? How can I get new ideas across? And more important, to be able to pass it to the kids. That it's a lifelong learning. It's a journey never ends. Just because you get a degree, it's a starting point for the next milestone. And you keep reinventing yourself. And by doing so, there's joy in doing new things. But the fundamentals has not changed. The physics are still there, the maths are still there, and therefore the foundation is necessary for you to be able to keep progressing and learning new things.
Can I do a demo?
1 minute.
Ma'am, just now you said that you're not so into physics. Can I ask for help? You look like the type who can sing. Yeah, you can sing. Yeah. You cannot sing, you should understand. Yeah. Then you can give me the paper. Yeah, I can sing. Okay, so this is a laser. Okay, so you have a drum. Alright, okay, and then do you see a mirror here? Do you see a mirror?
Yeah.
Do you see a mirror?
Yeah.
Yeah, okay. So if I speak inside, right, do you see like any vibrations at all? Any vibrations? Any vibrations? No? Yes? If you have super eyes, you can see. Do you have super eyes?
No.
No? Okay, yes? No. Okay, alright. Okay. So, but I'm going to bounce the laser beam off the mirror.
Okay.
Alright, and later on you're going to help me.
Okay.
Try.
Okay.
Yeah? Okay, just try. Alright, okay. So, but my voice is a bit lower, so you will try, alright? Okay, so I'm going to do this. I'm going to just get the laser beam bounce off the mirror, get it? Alright, okay, so I'm just going to do that. Okay. Then you see a spot.
Yes.
A spot over there. Okay. Okay, so now if I talk, right?
Yes.
Now you can't see much, right? I mean, as in the whole thing is bouncing all the time. But if I sing, then it's quite different. Ready?
Okay.
Do, do, do. You see a pattern?
Yes.
Do,
Yes.
re. You see a pattern?
Yes.
Re. Okay? It's all pattern. Mi, mi,
Square.
Mi, fa, sol, la, do. Okay, right? Okay? So you try, alright? Yes, different patterns. Good. Alright, okay. So then you try. Okay. Okay, so I'm gonna just actually it's better if you have lights a bit dim, alright? Okay.
So I shine it on the wall.
Don't worry, I'll help you.
Okay.
Yeah. Okay.
Shift
Okay.
dim the
So-
lights.
So okay. Okay, it's on the ceiling now.
Yes.
Okay, your voice is good.
Yes.
Okay, so can I sing do for us? Do you see that?
Yes, see.
Good. Okay, good. So you see pattern? Okay.
Oh, the top, the ceiling.
Good. So it's good. Okay, good. Okay, good. Alright, of course, when this thing vibrates, right? Okay, so if it's vibrating, it's super better. Alright, okay, so what we do? Maybe you just do this. Alright, okay, the mirror does this, and then this thing just do this, and you see some shape, right? But if it's bouncing a lot, alright, okay, so in a maybe different way, this way, maybe you just see this, and if it's fast, what do you see? You see here? Sort of a circle, right? Yeah, alright, okay, and of course, based on the patterns, then you can try to figure out how this thing is jiggling around. You get some idea of this? Okay. Okay, look. Yeah. Okay, sorry? Why? Okay. Okay, I passed. Okay. Okay. Very fast. Okay, so over here, okay, so if let's say that this thing is just bouncing this way. Alright, okay, and the mirror just goes over. Okay, the laser beam comes in, goes out. What do you think you will do? Maybe you will just do this. And if it's very fast, what is it? What is it? A line. Just a line, right? Okay, but if it's just doing this, alright, okay? So if it's something different, alright, okay? So let's say that this thing comes out, this thing goes in, this thing comes out, this thing goes in. Some different note. You're singing a different note, and then of course the vibration is different. Right? Maybe you have this, and it's very fast. Yeah, in a sense, yeah, right. Yeah, okay. Yeah. We can do the mathematics later, but okay. So you get some idea, right? Okay, so you have different kind of waves, right? Then the laser bounces, bounce on this, comes out, and then alright, maybe you get some different patterns. So different kind of waves, different kind of patterns. Different kind of patterns, different kind of waves. Okay? You get some idea? Good. Thank you very much. Alright.
So I just want to say one thing.
You didn't award her the marks 100.
900 for singing. 100. Physics got to, yeah, asking why, that is so much. Okay, right. Yeah, okay, yeah, I just want to make just one point. So we are all concerned about physics and physics in the community. I think the point that I want to make is perhaps we should not try to just preach to the choir too much. Thank you.
Well, I think we have to stop somewhere, so regretfully, I want to thank my panel members. They have really exceeded all our expectations. I just want to tell you one more story about engineers. I was once on a panel assessing research applications. I'm not going to tell you which funding agency. So one proposal came, I think, from an engineer technologist for some sort of lifting device. After looking at the thing for his diagram for about 10 minutes, I realized that it violated Newton's third law of physics. So I wrote on my assessment, throw it out, don't allow him to come back, violates Newton's third law of physics. To my amazement, next year, he resubmitted the same project, and he said, I may be able to prove Newton's third law of physics wrong. I'm not going to tell you which funding agency. Okay, you can ask me privately, I'll tell you. I shouldn't tell you. Okay. But it does show that, as our panel members have said, we're worried about examinations and all that, and students. But I think the more general point really to be made, and which they have made very well, is that physics is so fundamental that really everyone should have some basic knowledge of physics. You should understand why you're not floating to the air, you know, why do cyclists crash into barriers when going in circles and all that. And it is so important that I think that if we can, someone suggested the fact that perhaps we should bring all this down to an earlier stage. Maybe even the primary education syllabus could be revamped. I just want to tell you, and DC knows, we're concerned about decisions that Singapore is going to make regarding nuclear power maybe 10 years down the road. So I looked at the primary syllabus, I found that there's no mention of radiation or nuclear. We are concerned because when Fukushima happened, all of us were astounded by the degree of ignorance that policymakers and media people had about radiation. It was as though radiation was coming from fifth dimension outside. So I think I consulted with my colleagues. I said, maybe we go and put something in the primary syllabus. So I went to the curriculum people and said, can you just put 3 sentences like this? A, radiation is not from the fifth dimension, it's all around us. When it's in small quantities, like small quantities of fire, small quantities of water, it's not dangerous. It is only dangerous when there are large amounts of it. That's all I wanted to put. Then I found out to my amazement that changing the primary syllabus is harder than changing the defense policy of Singapore. As DC said, we're still trying all these things out, actually. So anyway, I want to thank not only the panel members, but members of the audience for your stimulating questions. And I hope that this is a very good start for the launch of the journal, and we will see a renewed interest in physics, not only among teachers and students, but among the general public as well. Thank you.